Right now, something invisible is racing toward you at nearly the speed of light. It has crossed thousands of years of empty space, survived collisions with magnetic storms bigger than entire star systems, and in the next second, it will slam into the atmosphere above your head without you ever knowing it happened. This is not science fiction. It is happening constantly every single day to every person on Earth. We call these visitors cosmic rays, and for over a century, they have been one of the strangest unsolved mysteries in all of physics. Nobody knew where they were born. Nobody knew what could possibly fling matter across the galaxy with so much force. And yet, buried in the data of a mountain observatory in China, scientists have finally started pulling back the curtain on the most extreme particle accelerators nature has ever built. What they found is stranger, more violent, and more powerful than anyone predicted. So stick around, because by the end of this video, you will understand exactly what is attacking our planet from deep space, and why some scientists now believe the Milky Way is a far more dangerous place than we ever imagined. Let's start with the basics. Space might look calm and silent from where we stand, but it is anything but peaceful. Scattered across the galaxy are objects that behave like natural machines, flinging subatomic particles outward at speeds so extreme that our best laboratories on Earth cannot come close to matching them. These particles are mostly protons, the stripped-down cores of hydrogen atoms, although some are heavier atomic nuclei, and a smaller fraction are electrons. Whatever their identity, they share one trait in common: they are moving at nearly the speed of light itself. When one of them slams into our atmosphere, it doesn't just disappear quietly, it triggers a cascade, a shower of secondary particles, muons, electrons, positrons, and gamma rays that rains down toward the surface. Most of this shower is harmless to us walking around down here, protected as we are by kilometers of thick atmosphere and a planetary magnetic field acting like an invisible shield. But that shield gets thinner the higher you travel, and it is not harmless to everything we build. Satellites in orbit take the hit directly. A single high-energy particle striking a sensitive circuit can corrupt data, scramble a system, or in the worst cases, fry the electronics completely, sometimes ending a mission worth hundreds of millions of dollars in an instant. Astronauts face an even greater risk, since prolonged exposure to this kind of radiation can damage living cells, raise the risk of long-term health problems, and complicate any future plans for extended missions to the Moon or Mars. Down here on the surface, the secondary particles produced by cosmic ray showers can even interact with living tissue, occasionally contributing to genetic mutations. In other words, this bombardment is not just an academic curiosity. It is a real ongoing hazard for anyone or anything operating beyond the protective blanket of our atmosphere. And understanding it is quickly becoming essential for the future of space travel. The story of how we discovered these particles is almost as strange as the particles themselves. Back in 1912, a young Austrian physicist named Victor Hess set out to solve a much smaller mystery. At the time, scientists had detected a faint background of radiation in the air and assumed it must be leaking out of the ground, most likely from radioactive elements in the Earth's crust. If that theory were true, then the higher you traveled above the surface, the weaker that radiation should become. Hess decided to test this directly, and he did it in the most dramatic way possible for the era. He climbed aboard a hot air balloon and rode it up into the sky, carrying instruments designed to measure the rate at which the surrounding air was becoming electrically charged, a process called ionization. As he ascended past a few thousand meters, he expected the readings to drop. Instead, they climbed. By the time he reached over 5,000 meters above sea level, the ionization rate was roughly 3 times higher than it had been on the ground. That result made no sense under the old theory. If the radiation were coming from the Earth, it should have faded with altitude, not intensified. Hess had stumbled onto something nobody expected. The radiation wasn't rising up from below him. It was raining down from above, from somewhere far beyond our planet. He had just discovered cosmic rays, although at the time, nobody had the faintest idea what could possibly be producing them. Hess would go on to win the Nobel Prize in Physics for this discovery, but at the time, nobody, including Hess himself, understood the true scale of what he had found. Later research would reveal that these particles were not just energetic. They were among the most energetic objects ever measured by human instruments, dwarfing anything produced by radioactive decay or ordinary stellar processes. That single balloon flight opened up a mystery that would haunt astrophysicists for the next 100 years. The problem is that cosmic rays are almost impossible to trace back to their source. Because most of them carry an electric charge, they get pushed and pulled by every magnetic field they pass through on their journey across the galaxy. By the time one of these particles reaches Earth, its path has been bent and twisted so many times that it no longer points anywhere near its true origin. It is a little like trying to figure out where a pinball came from after it has bounced off 100 different obstacles. On top of that, cosmic rays don't survive contact with our atmosphere in their original form. The moment they collide with air molecules, they shatter into a spray of secondary particles, destroying any direct evidence of what the original particle actually was. So for scientists, hunting cosmic rays has always meant working backward from wreckage, trying to reconstruct a crime scene using only fragments and debris. This challenge becomes even more obvious when researchers study something called the cosmic ray spectrum, which is essentially a graph plotting how many particles arrive at each energy level. Instead of a smooth, predictable curve, the graph bends sharply at a certain point, a feature scientists nicknamed the knee. Beyond this knee, particles with energies above roughly 4,000 trillion electron volts become dramatically rarer. For decades, nobody could agree on what this bend actually meant. Some researchers guessed it marked the boundary between cosmic rays born inside our own galaxy and those arriving from somewhere far beyond it. Others simply admitted they had no idea. The knee sat there in the data for generations, a stubborn clue that refused to give up its meaning. Just when it seemed like the trail had gone cold, a new kind of observatory changed everything. High in the mountains of Sichuan province in China, at an altitude of roughly 4,500 meters above sea level, scientists built something called the Large High Altitude Air Shower Observatory, known by its acronym LHAASO. Its mission was singular and ambitious: to catch the highest energy particles the universe could throw at us. According to the observatory's chief scientist, Professor Tan Cao, solving the mystery of the cosmic ray knee required two things above all else. First, the detector needed to be enormous, because the highest energy particles are almost unbelievably rare, arriving at a rate of less than 1 per square kilometer every single century. Second, the observatory needed the ability to actually identify what kind of particle triggered each shower, whether it was a simple proton, a heavier helium nucleus or something else entirely. To meet the first requirement, the team built an array spanning an area roughly equivalent to 190 football fields. To meet the second, they layered in at least 3 different types of interconnected detectors, each one designed to catch a different piece of the shower and help scientists piece together the full picture of what had originally struck the atmosphere. One set of detectors tracks the muons produced deep within a shower. Another measures the electromagnetic component spreading across the surface, and a third captures faint flashes of Cherenkov light, a kind of optical shock wave produced when particles move through the atmosphere faster than light itself can travel through that same medium. Combining all 3 data streams lets researchers reconstruct not just how much energy a particle carried, but what type of particle it most likely was, something no single detector could achieve alone. The location itself was chosen carefully too. Sitting at 4,500 meters above sea level means the air is thinner, so a shower reaches the detector array closer to its peak intensity before it has a chance to fade out, giving scientists a clearer, sharper signal to work with. It didn't take long for this approach to pay off. According to Professor Cao, the observatory hadn't even been fully completed. Only about half of the planned detector array was operational when the team noticed something extraordinary. An enormous number of gamma rays were pouring in, far more than anyone had anticipated. By 2021, the data confirmed it. LHAASO had picked up gamma ray photons crossing the 1 quadrillion electron volt threshold, and one single photon that reached an almost impossible 1.4 quadrillion electron volts. To put that number into perspective, it was nearly 150 times more energetic than the fastest protons ever produced inside the Large Hadron Collider, humanity's most powerful particle accelerator. This wasn't just a record. It was proof of something scientists had theorized about for decades, but never confirmed. Energy at that scale cannot simply appear out of nowhere. The laws of physics demand a source, something out in the cosmos capable of pumping particles up to these staggering energies. Researchers had a name ready for this hypothetical class of object. They called it a Pevatron, a source powerful enough to accelerate matter to a peta-electron volt of energy and beyond. LHAASO had just proven once and for all that Pevatrons were real. Confirming that Pevatrons existed was only the first step. The much harder question was figuring out where they were hiding. This is where gamma rays became an unexpected gift to scientists. Unlike charged cosmic ray particles, gamma rays carry no electric charge at all, which means magnetic fields cannot bend their path. They travel in perfectly straight lines across the galaxy, like arrows fired from a bow. That property gave LHAASO's team a rare opportunity, the chance to trace a detected gamma ray straight back to the patch of sky it came from. Scanning their data, researchers pinpointed 12 distinct locations capable of producing these ultra-high energy gamma rays, several of which showed clear evidence of accelerating particles all the way up to a full quadrillion electron volts. But there was still a catch. Knowing the direction a gamma ray came from is not the same as knowing how far away its source actually is. 12 lines of sight stretching endlessly outward into deep space could, in theory, point to objects anywhere from the edge of our own galaxy to distant galaxies billions of light years away. Fortunately, scientists had one more trick up their sleeve. The universe is filled with leftover photons from the Big Bang, an ancient, extremely low-energy glow that fills every corner of space. When an ultra-high-energy gamma ray happens to collide with one of these ancient background photons, it doesn't survive the encounter. It gets destroyed. This means gamma rays at these extreme energies simply cannot travel enormous distances without being wiped out along the way. If LHAASO was detecting them here on Earth, that placed a hard limit on how far they could have traveled. The math ruled out an origin beyond our own galaxy entirely. Every single one of those 12 mysterious sources had to be hiding somewhere inside the Milky Way. Suddenly, the search area shrank dramatically, and with it, the knee in the cosmic ray spectrum finally made sense. It had nothing to do with particles arriving from other galaxies. The real story was unfolding much closer to home. This was a genuinely humbling moment for the field. For decades, some of the smartest minds in astrophysics had debated whether the knee marked a doorway to the wider universe, a boundary separating our galaxy from everything beyond it. Instead, the answer turned out to be sitting quietly among the stars we can see with our own eyes on a clear night, hidden in plain sight the entire time, with the hunting ground narrowed down to our own galactic backyard. Scientists could finally focus on the real question: what kind of object is powerful enough to become a Pevatron? Space is full of extreme environments, and researchers had several strong suspects in mind long before LHAASO confirmed anything. The first and most obvious candidate was the leftover wreckage of a dying star, a supernova remnant. For roughly 70 years, this had been the leading theory in the field. The reasoning is straightforward. When a massive star explodes, it hurls material outward into interstellar space at tremendous speed, creating a violent shockwave that plows through the surrounding gas. Charged particles caught near this shock front get bounced back and forth across it repeatedly, gaining a little more energy with every pass, sometimes for thousands of years. This process, known as diffusive shock acceleration, can theoretically supply most of the cosmic rays observed throughout our galaxy, if even a modest fraction of the explosion's kinetic energy gets converted into accelerated particles. There is, however, a serious limitation. Models suggest that a supernova remnant can only reach these extreme peta-electron volt energies during the first century or so after the explosion. Every supernova remnant we currently know of is far older than that, which makes pure supernova acceleration an awkward fit for what LHAASO was seeing. There is one loophole, though. If particles inside a young remnant build up enough energy to break free of its confining magnetic fields, they can escape and slam into nearby giant clouds of gas, generating powerful gamma rays even after the remnant itself has aged past its peak acceleration window. Roughly half of LHAASO's 12 original candidates line up with supernova remnants in this indirect way, making them a meaningful, if imperfect, piece of the puzzle. The second candidate turned out to be even more promising, and it comes from one of the strangest objects in the entire universe, the pulsar. A pulsar is the collapsed, ultra-dense core left behind after a massive star explodes, a neutron star spinning at incredible speed while generating an intensely powerful magnetic field. Astronomers have now catalogued more than 1,500 of them across the sky. These spinning stellar corpses are already known to be excellent at accelerating electrons and positrons, because their rotating magnetic fields generate electric fields strong enough to rip charged particles straight off the star's surface. This creates a fast-moving wind of particles streaming outward from the pulsar. When that wind eventually slams into surrounding material, whether it's leftover gas from the original explosion or interstellar dust, it abruptly decelerates, forming what scientists call a termination shock. Right at that boundary, particles get kicked up to extraordinary energies. In much the same way, water rushing through a narrow channel speeds up dramatically when it hits an obstacle and gets forced through a tighter gap. According to LHAASO's research team, more than 30% of their candidate Pevatrons appear to be linked to pulsars, making them arguably the single most important player uncovered so far in the search for the origin of cosmic rays. Then there is a third, far stranger possibility, one that surprised even the scientists studying it. When researchers zoomed in closely on the shape of the knee in the cosmic ray spectrum, they didn't find a smooth curve. They found a hump, an anomaly that didn't behave the way particles from supernova remnants or pulsars typically do. This forced the field to think beyond the traditional suspects and consider something far more exotic: black holes acting as natural particle accelerators. The theoretical foundation for this idea traces back to 2009, when physicists described what became known as the Bañados-Silk-West effect. The concept is almost unbelievable. If two particles fall toward a black hole from just the right angle and collide extremely close to the event horizon, the collision could, in theory, produce almost unlimited amounts of energy. For years, this remained a fascinating but mostly academic idea, since any particles produced this way seemed destined to simply fall into the black hole and vanish forever. More recent modeling changed that assumption. It turns out a meaningful fraction of these newly energized particles can actually be flung back outward into space rather than swallowed. Once free of the black hole's grip, these particles would travel across the galaxy exactly like the cosmic rays we detect here on Earth, meaning that some of the most extreme objects in the universe might double as some of its most extreme particle factories. Theory is one thing, but actually pointing a finger at a real object in the sky is another challenge entirely. So which specific Pevatrons have scientists actually managed to identify? One of the very first confirmed candidates is an object many people already recognize, the Crab Nebula, also catalogued as Messier 1. It sits roughly 6,500 light years from Earth in the constellation Taurus, and it is the glowing remnant of a supernova explosion. Despite its beauty, the Crab Nebula is far from a peaceful sight. It is capable of accelerating electrons all the way up to a full quadrillion electron volts, and because it is one of the most thoroughly studied objects in the sky, it has become a natural laboratory for understanding exactly how these cosmic accelerators operate. In the gamma ray range, the Crab Nebula shows dramatic, unpredictable flaring behavior, sudden bursts of brightness that can last anywhere from a few hours to several days. Scientists now understand these flares as direct evidence of intense electron acceleration happening in real time, though the precise mechanism behind them is still debated. It could involve shock acceleration at the boundary between the pulsar's particle wind and the surrounding nebula, energy released when tangled magnetic field lines snap and reconnect, or some more complicated process happening deep within the wind itself. What is clear is that producing a gamma ray with a quadrillion electron volts of energy requires an electron carrying several times that amount to begin with, which confirms without much doubt that the Crab Nebula is a genuine Pevatron, and an especially efficient one. There is an important caveat here, though. This only proves the Crab Nebula accelerates electrons. Scientists specifically want to find sources capable of accelerating protons, since protons make up the majority of the cosmic rays raining down on Earth. Finding a proton Pevatron, sometimes called a hadronic accelerator, became the next major goal. That search led directly to one of the most intriguing regions in the northern sky, the constellation Cygnus. Spanning more than 800 square degrees, an area equivalent to roughly 4,000 full moons side by side, Cygnus turned out to be hiding exactly the kind of extreme energy scientists were chasing. LHAASO detected an enormous number of peta-electron-volt photons streaming from a region known as the Cygnus cocoon, a vast bubble of gas surrounding an active zone of star formation. At the heart of this bubble sits a massive cluster of young stars called the Cygnus OB2 Association, located nearly 5,000 light-years from Earth. These young, massive stars generate ferocious stellar winds capable of accelerating particles, and their location lines up remarkably well with the gamma-ray signals LHAASO detected. But remember, gamma rays only reveal a general direction, not an exact distance, and the Cygnus region happens to be crowded with energetic candidates. Sitting further along roughly the same line of sight is another suspect entirely, an X-ray binary system called Cygnus X3. This system pairs an extremely hot, massive Wolf-Rayet star with a compact companion, most likely a black hole or neutron star, locked in orbit together. Material streams from the donor star into the compact object through powerful stellar winds. While the compact object fires off jets of superheated plasma, creating exactly the kind of violent environment needed to accelerate particles to extreme energies. For a while, scientists genuinely couldn't tell whether the peta-electron-volt signal was coming from the young star cluster or from this binary system. The breakthrough came when researchers noticed something subtle hiding inside the data, a repeating pattern showing up not just in the gamma rays, but simultaneously in X-ray and infrared observations too. Every 4.8 hours, the signal pulsed in a consistent rhythm. That number turned out to be the key. 4.8 hours is exactly how long it takes the compact object in Cygnus X3 to complete one orbit around its massive companion star. The mystery was solved. The gamma rays really were coming from Cygnus X3, confirming it as a genuine Pevatron in its own right. What made this discovery even more remarkable was the sheer scale of the energy involved. The highest energy photons detected from this system measured an incredible 3.7 peta-electron volts, and since these photons are radiated by accelerated protons, the protons themselves had to carry several times that much energy to begin with. This places Cygnus X3 in an entirely different category, not just a Pevatron, but what scientists now call a super-Pevatron, capable of accelerating protons to at least 10 peta-electron volts, deep into the territory of the most extreme cosmic rays we've ever recorded. Think about what that actually means for a moment. A system barely larger than our own solar system, sitting quietly among the stars of Cygnus, is somehow acting as a natural machine more powerful than every particle accelerator humans have ever constructed combined. The idea that a stellar mass black hole locked in a tight orbital dance with a dying star could outperform the Large Hadron Collider, an instrument that took decades and billions of dollars to build, says something profound about just how much raw power is quietly at work across our galaxy, far beyond anything we've learned to harness ourselves. From here, the discoveries didn't slow down, they accelerated. What started as a short list of just 12 mysterious sources has grown dramatically in only a few years. In 2023, LHAASO published the first global catalogue of galactic Pevatrons, listing 43 confirmed ultra-high-energy gamma-ray sources scattered across the Milky Way. Just 2 years later, thanks to continuous monitoring from observatories around the world, that number has climbed past 75. Every new addition to this list chips away at an old and comforting assumption, the idea that our galaxy is a relatively calm, quiet place compared to more violent galaxies elsewhere in the universe. Many astronomers once believed the Milky Way lacked the kind of extreme, energetic environments found in galaxies with supermassive black holes tearing through their cores. LHAASO's growing catalogue has quietly demolished that assumption. Our own galactic neighborhood is turning out to be filled with natural particle accelerators more powerful than anything humanity has ever built, hidden in plain sight among the stars we've been looking at for centuries. This isn't a solo effort either. LHAASO now works alongside a growing international network of observatories detecting high-energy gamma rays, including facilities in the United States, Germany, Namibia, and Spain. Some of these instruments use giant water tanks buried underground to catch the faint Cherenkov glow of passing particles, while others use fields of mirrors pointed at the night sky to capture the same optical shock waves from a completely different angle. Even neutrino observatories, built to catch nearly massless particles that pass through entire planets without slowing down, have joined the search, since some of the same violent environments that accelerate cosmic rays are expected to produce high-energy neutrinos as a byproduct. By comparing notes, sharing data, and cross-checking each other's detections, this global collaboration is slowly building a complete picture of the non-thermal universe, the hidden layer of extreme energy that our eyes were never designed to see. And this matters far beyond pure curiosity. Understanding where cosmic rays come from helps us predict and prepare for the radiation environment our satellites and astronauts have to survive in. It sharpens our understanding of how energy moves through galaxies, how magnetic fields are structured across vast stretches of space, and how matter behaves under conditions no laboratory on Earth could ever safely recreate. It even connects to some of the deepest open questions in fundamental physics, since these natural accelerators are reaching energies our best human-made machines, including the Large Hadron Collider, cannot even approach. In a strange way, the galaxy itself has become the biggest and most powerful particle physics laboratory we will ever have access to, and we are only just beginning to learn how to read its results. Of course, plenty of mysteries remain. Scientists still don't know the exact identity of every single Pevatron on that growing list of 75 candidates. Pinning a gamma-ray signal to one specific object, especially in crowded regions like Cygnus, remains an enormous challenge. Nobody fully understands how particles manage to escape the powerful magnetic fields that should, in theory, trap them near their source. And the black hole acceleration mechanism, while theoretically sound, has yet to be confirmed with the same level of certainty as supernova remnants and pulsars. There are also hints of even more extreme particles out there, cosmic rays reaching energies so far beyond a peta-electron volt that scientists aren't entirely sure what kind of object could produce them at all. Some ultra-high energy events recorded by other detectors around the world have carried energies in the x-electron volt range, 1,000 times beyond even the most powerful Pevatrons discovered so far, and their origin remains almost a complete mystery. Somewhere out there, an even more powerful class of accelerator, something beyond even the black holes and pulsars we've identified, may be waiting to be discovered. Some researchers even wonder whether entirely new physics might be needed to explain the very highest energy cosmic rays ever detected, particles so energetic that a few individual protons have been recorded carrying roughly the same kinetic energy as a fast-pitched baseball compressed into a single subatomic particle. Figuring out what could possibly produce that kind of energy remains one of the great open frontiers of modern astrophysics. And the next generation of detectors, larger, more sensitive, and more widely distributed across the globe, are being built right now specifically to chase it down. There is also the question of scale and time. Every Pevatron discovered so far represents a brief, cosmically speaking, snapshot of a process that has likely been running since the galaxy first formed billions of years ago. Supernova remnants fade, pulsars slow down, and binary systems eventually evolve into something else entirely, which means the population of active Pevatrons lighting up the sky today is constantly changing. Some of the sources LHAASO detected may have already faded into quieter, less energetic states by the time you watch this video, while new ones are almost certainly flaring to life somewhere in the galaxy right now, completely undetected. This turns the hunt for cosmic ray sources into a moving target, one that requires constant monitoring rather than a single definitive survey. It also raises a fascinating possibility that the total number of Pevatrons hiding in the Milky Way could be far higher than the 75 candidates identified so far, with dozens more simply too faint, too distant, or too well hidden behind gas and dust for our current instruments to catch. For over 100 years, cosmic rays fell to Earth as an unsolved riddle, an invisible barrage from an unknown enemy hiding somewhere in the dark. Today, thanks to a mountaintop observatory in China and a growing web of detectors spanning the globe, we are finally starting to identify the culprits. Dying stars, spinning neutron stars, and possibly even black holes themselves are acting as nature's own particle accelerators, hurling matter across the galaxy faster than anything humans have ever managed to build. The fastest matter in the known universe isn't coming from some distant alien civilization. It's being forged right here inside our own galaxy by the most violent objects nature has ever created. And every single day, a tiny piece of that violence reaches all the way down to us. And this is really just the beginning. As more high-altitude observatories come online, and existing ones like LHAASO continue collecting data year after year, the catalogue of confirmed Pevatrons is only going to keep growing. Each new entry adds another piece to a puzzle that took over a century just to properly define. We now know cosmic rays are real. We know roughly where the highest energy ones in our galaxy are coming from. And we have identified 3 genuinely plausible mechanisms capable of producing them. What remains is the painstaking work of matching every single signal to its exact source, untangling crowded regions of the sky where multiple candidates overlap, and pushing our detectors to catch fainter, more distant, and even more extreme events than anything recorded so far. Somewhere out there, hidden among the 75 known candidates and the countless more still waiting to be found, might be the answer to an even bigger question: just how much energy is nature truly capable of producing? And have we even come close to finding its upper limit If this journey into the hidden, high-energy side of our galaxy blew your mind, make sure you hit that subscribe button so you never miss the next deep dive into the mysteries of the universe. Drop a comment below and let us know where in the world you're watching this from. We love seeing just how far this curiosity travels. And if you're hungry for more, check out another video on this channel and keep exploring the universe with us.